Okay, good afternoon to all. And in this session, we'll be discussing on nonlinear finite element analysis of reinforced concrete beam using the software ABAQUS. Now, before going directly into the software and discussing the modeling and all, first let us understand some basic concepts on the concrete behavior and all. Now, coming to the introduction. Now, why do we do finite element modeling? Now, FE modeling provide a predictive model for structural failure and expand the range of experimental data and provide information on key phenomena in the absence of any experimental data. See, to actually get a behavior of any structures, you need to do an experimental test. But conducting experiments every time is not practicable. It is extremely time consuming, and also the use of material sometimes will be very expensive. Now, the use of computer software to model structural elements has now become much faster and extremely cost effective. The use of finite element softwares helps to handle very complex and complex geometries. This is actually the heart and power of FEM. It can also handle varieties of engineering problems like starting from the solid mechanics, dynamics, thermal problems, fluid mechanics, and even electrostatic problems. It can also handle complex restraints like indeterminate structures can be solved. And of course, complex loading as well, like point loads, element loads, thermal loads, even inertia forces, and also time frequency dependent loadings. Now coming to nonlinearity. Basically, there are three classical nonlinearities. The first one is the geometric nonlinearity. So any changes in the geometry of the structure during the analysis, such as when you have large displacement, or you have preload or load stiffening, or sometimes instability like snap through in very thin structures, in flexible structures, you need to consider geometric nonlinearity. An example of geometric nonlinearity is shown in the figure. You can see the deformation is very large, such that this deformation may affect the results. The second type of nonlinearity is the material nonlinearity. See, most of the metals have linear stress strain relationship at low loads, but at higher loads, the material starts to yield, due to which the response become nonlinear. Now, this is an example of stress strain relation for a rubber. For a material like rubber, it initially itself you have a nonlinear response. The third type is not very common, but still you have boundary nonlinearities. Boundary conditions sometimes change during the analysis. So you can, an example of nonlinearity in the boundary condition is here. You have a cantilever beam and have a support at the end, which is not actually touching, but at some distance below the beam. So at initial load, this cantilever beam, this beam will behave like a cantilever. But when this end touches the support, the stiffness actually changes, which in turn the response becomes nonlinear. So such conditions may arise where you need to consider the boundary nonlinearity. Now in the present session, we will be discussing only the material nonlinearity. Now coming into concrete, we know that concrete, unlike steel, is not homogeneous. Concrete is a particulate composite of large aggregate and mortar mix. That is a composite of sand and cement. And the physical behavior is also rather complicated, and it strongly depends on many factors like water cement ratio, aggregate size, shape distribution, cement type, temperature, and much more. So we consider concrete to be homogeneous and initially isotropic. In reality, we have a vast number of micro cracks at the aggregate boundaries itself due to shrinkage and very complicated stress strain even before we put any load to the concrete structure. So modeling concrete is very complex. It has an nonlinear stress strain relation in multi-axial. It has a strain softening behavior. You have progressive crack formation. In reinforced concrete, you have pull-out reinforcement, aggregate interlocking, etc. And also, you may sometimes need to consider time-dependent behavior like creep or shrinkage. The compressive response of concrete is highly nonlinear and can be described numerically using several approaches. Some of them are by representation of stress strain relation by curve fitting method, which most of the IS standards, the standard codes follows. You can also model the behavior of concrete using elasticity theories or even plastic theories. Now coming to concrete cracking. Now in modeling you have two types of crack models. First one is the discrete crack model and the smeared crack model. In discrete crack model, it relies on simulating individual cracks as geometric identities within a model by introducing discontinuities within a finite element mesh at element boundaries. Whereas in smeared crack models, the crack material is treated as continuum and the deterioration caused by the crack is spread across the element by changing the element stiffness, which is often called as strain softening. So in a smeared crack model, it does not track individual macro cracks. So here the constitutive calculations is performed independently at each integration point of the finite element. And the presence of the crack enters into this calculation by the way in which the cracks affect the stress and material stiffness associated with the integration point. So in ABAQUS, both are available, but this discrete crack models is more advanced. So we'll be considering only the smeared crack model. So in ABAQUS, you have two models for concrete, the concrete damage plasticity model and the concrete smeared cracking model. So let's briefly see what are these models. It's not possible to describe each and every term related to modeling this two. Anyway, because these are very advanced topic, plasticity and all. Anyway, I'll go through briefly through these topics. Now, this concrete damage plasticity model provides a general capability for modeling concrete and other quasi-brittle materials. It is a continuum plasticity-based damage model for concrete. And it assumes two failure mechanisms, tensile cracking and compressive crushing of concrete material. This model is based on the yield surface, which is controlled by two hardening variables, which is related to the failure mechanism under tension and compression. And these variables are referred as tensile and compressive equivalent plastic strains. Even though this model is intended for reinforced concrete, this can be used for plain concrete as well. And also this model can be used when concrete is subjected to monotonic, cyclic, or even dynamic load at very low confining pressures. This model consists of combination of non-associated multi-hardening plasticity and scalar damage elasticity to describe the irreversible damage that occurs during the fracture process. This can be defined to be sensitive to the rate of straining as well. And it requires that the elastic behavior of the material to be isotropic and linear. Now, to define this model, you have certain input parameters. You need to input some plasticity parameters like dilatation angle, eccentricity, ratio of stresses, the parameter K, the viscosity parameter, And of course, the response of concrete to uniaxial loading in tension and as well as compression. Now let's see briefly what are each of these terms. So the yield surface which is used for the concrete damage plasticity model is actually a modified Drucker-Prager strength hypothesis. This figure shows the failure surface for according to Drucker-Prager strength hypothesis. Now this model has been further modified by many other authors. So according to the concrete damage plasticity model, the modification is such that the failure surface need not be a circle. And this shape is governed by the parameter K. So when K is about 2/3, it takes a shape of like this. It's not a triangle, but a combination of 3 ellipses. So physically K is the ratio of second stress invariant on the tensile meridian to that one on the compressive meridian. And this K takes the value from 0.5 to 1. When K is equal to 1, you have a circle. So for ordinary concrete, the default value is 0.67. Similarly, the shape of the plane's meridian in the stress spaces changes. So this is the hydrostatic plane and the deviatory plane. In this is not a straight line. For classical Drucker-Prager theory, this is a straight line, whereas for CDP model, it is curved. Here, the model assumes that the plastic potential surface in the meridian plane assumes the form of hyperbola. So this distance need to be given, which is called as eccentricity. So this can be interpreted as ratio of tensile strength to compressive strength. And this, the default value is 0.1. Again, you also have another parameter called dilatation angle. This angle is the angle of inclination of the failure surface towards the hydrostatic axis measured in the meridional plane. And physically, this angle is interpreted as the concrete internal friction angle. For ordinary concrete, you can take the angle as 36 or 40 degree. Now, another parameter describing the material state is when it undergoes biaxial compression. FB0 by FB0. It is the ratio of biaxial to uniaxial compressive strength. Now, based on the experiments conducted by Kupfer in earlier 1969, he approximated with the elliptical equation that the uniform biaxial compressive strength is actually equal to 1.16 times the uniaxial compressive strength. So hence, for ordinary concrete, you can take a value of 1.16. The last parameter describing is the viscoelastic regularization. Here, we are actually modeling softening behavior of the concrete as well. So there is a stiffness degradation. Due to stiffness degradation, since we are using numerical techniques for solving the problems, you may have convergence difficulties. So viscoplastic regularization of constitutive equation causes the consistent tangent stiffness of the softening material to become positive for sufficiently small time increments. So when you have convergence issues, you can use viscosity parameter for smoothly running the program. So default value is 0. Now coming to the response of concrete to uniaxial loading in compression. You have to input stress strain relation for concrete. This you will get from the experimental data. You can conduct experiments on cylinder and get the stress strain relation. So under uniaxial compression, the response normally is linear until the initial yield sigma 0. And in the plastic regime, The response is typically characterized by stress hardening, followed by strain softening beyond the ultimate stress sigma c. So it is assumed that the uniaxial stress strain curve can be converted into stress versus plastic strain curve. This conversion is done automatically by the ABAQUS using this equation. The epsilon c plastic is equal to epsilon c inelastic minus dc by 1 minus dc into sigma c by, where dc is the degradation variable or damage parameter, which is a function of plastic strain, temperature, and other field variables. Now this damage parameters varies from 0 to 1. Now when concrete is unloaded from any point in this strain softening branch, you can see the unloading response is weakened. The elastic stiffness of the material appears to be damaged or degraded. So the degradation of the elastic stiffness is actually characterized by this damage variable dc. So in literatures you can see different methods for describing this dc versus plastic strain. In some literatures they take the ratio of the stress beyond the inelastic stress to the peak stress, or sometimes it is taken as the ratio of strain to the total strain. And in some other literatures, they use energy concepts for defining this damage parameter. Now, of course, you also have to input response of concrete in use to uniaxial loading and tension. Now, conducting tension on concrete is very difficult. So people go for indirect methods like split tensile strength and all. So if the data for uniaxial loading and tension is not available, you can use different models available in literature for modeling the response under tension. So here also under uniaxial tension, the stress strain response follow a linear relationship up to the failure stress. Now this failure stress corresponds to the onset of micro cracking in concrete material. And beyond the failure stress, the formation of micro cracks is represented macroscopically with a softening stress strain response. Normally, this induces strain localization in the concrete structure. See, concrete, we normally say concrete is brittle, and concrete in tension is not actually treated as elastic brittle body. You have to take into the phenomenon such as aggregate interlock, and when it is a reinforced concrete, you have a rebar like a bond slip, dowel action, etc. So to take into account of these phenomena, the decrease in the stress in the concrete in the tension zone should not occur suddenly, but gradually, so that you can consider this aggregate interlock, the interaction between the reinforcement and concrete and all can be considered if you consider this portion. This is sometimes called as tension stiffening. So even cracked concrete can take some tension. This also helps in avoiding numerical inconsistencies. So in ABAQUS enforces the user to give a very low stress value, very low post failure stress, which is equal to around 1/100th of the initial stress. So that much value you have to give so that you can run the problem very smoothly. The second, so that is all about the concrete damage plasticity model. Coming to concrete smeared cracking model. This model is also used for modeling concrete of all type, like beams, trusses, shells, solids. Now, unlike the damage plasticity model. Here you can use only for monotonic strain. You cannot use for cyclic loading, this model. And in this model, it consists of isotropically hardened yield surface that is active when the stress is dominantly compressive, and it has an independent crack detection surface that determines if points fail by cracking. And this model uses oriented damage elasticity concepts, smeared cracking, to describe the reversible part of the material's response after cracking. Now in this model, the input parameters are, of course, the response of concrete to uniaxial loading and compression. You require some failure ratios, tension stiffening data, and shear retention. Now let us see what are all these parameters in brief. So concrete response in compression, as we have seen before. Here what we need to note is that initially you have a straight line, then you have a strain hardening, beyond which it reaches an ultimate stress, beyond which you have a strain softening. Now here, if the load is removed at some point after inelastic straining, the unloading response is softer than the inelastic response. The elasticity is actually damaged. This effect is ignored in this model, since we assume that the applications involve primarily monotonic straining. So here, when you unload at any point, you have a stiffness which is equivalent to the initial stiffness. So you cannot use this model for reverse loading. Now the response of concrete under uniaxial tension. So here the uniaxial concrete specimen is loaded in tension. Normally the tensile strength is typically 7 to 10% of the ultimate compressive strength. When it reaches 7 to 10% of the compressive strength, the concrete starts to crack. So the model assumes that cracking causes damage in the sense that open cracks can be treated as the loss of elastic stiffness. And here tension stiffening is used to define the strain softening behavior of cracked concrete. So for reinforced concrete, you need to define stress strain tensioning stiffening model. So here strain softening after failure reduces the stress linearly to zero at a total strain of about 10 times the strain at failure. Normally a standard concrete fails at a strain of 10 raised to minus 4. So 10 times means 10 raised to minus 3. So you can give a linear variation from here to here for defining tension stiffening curve. Now in smeared cracking model, the yield surface is defined by some failure ratios. In multi-axial stress phase, these observations are generalized through the concept of surfaces of failure and flow in stress phase. So this is the stress rate in plane stress. Now let's see what are the failure ratios required to define the shape of the failure surface. You need the ratio of ultimate biaxial compressive stress to ultimate uniaxial compressive stress. See, actually to get the biaxial compressive stress experimentally is difficult. If you are not having any of these values, you can take the default values if you are using an ordinary concrete. But when you use different concrete like high performance, fiber reinforced, you need to give a different value. The biaxial compressive stress may change. The absolute value of the ratio of uniaxial tensile stress at failure to ultimate uniaxial compressive strength. Then the third ratio is the ratio of magnitude of principal component of plastic strain at ultimate stress in biaxial compression to the plastic strain at ultimate stress in uniaxial compression. And the fourth ratio is the ratio of tensile principal stress at cracking in plane stress when the other principal stress is at the ultimate compressive value to the tensile cracking stress under uniaxial tension. ABAQUS has given default values for these four ratios. So if you are If the data is not available, you can use the default values. Now the last parameter for defining the smeared cracking model is the shear retention. The shear retention factor refers to the amount of shear transfer across the crack. It is shown that combined tension and shear experiments, when used to calibrate the post-cracking shear behavior, these experiments are quite difficult to perform, the combined action of shear and tension. So the shear retention factor goes linearly to zero at same crack opening strain used for tension stiffening model. When you have a shear retention factor of 0, it refers that you have no aggregate interlock. Whereas when you give 1, it represents full aggregate interlock. So the shear retention factor varies from 0 to 1. Okay, this comes to the end of the modeling parameters. Now we'll discuss how to model this using the software. Now for that, I have taken 2 examples. So we'll consider a simply supported beam under flexure and shear. Now for flexure loading, we'll consider a point load acting at the center. And for shear loading, we'll consider a 2-point load, which is having a shear span of 1.25 meter. Now again for flexure loading, we'll consider 4 reinforcement at bottom, tensile reinforcement, and 2 8 mm bars at top, and also shear stirrups. And for shear behavior, we'll give only tensile reinforcement. We won't give any the stirrups or top bars, so that we can initiate shear failure. Here we can initiate flexure failure. Now for modeling this concrete, I have used the stress strain relation in compression and tension. The first graph shows the stress strain relation in compression. So this stress strain relation is for concrete having a compressive strength around 28 Newton per mm square. And this is the response of concrete under uniaxial tension. The elastic properties, we'll consider E as 22 gigapascal and Poisson's ratio as 0.2. This I have taken from the literature. Of course, as I said before, for concrete damage plasticity model, we need to input damage parameters. So this damage parameter is a function of inelastic strain for concrete in compression, and cracking strain for concrete in tension. And this value varies from 0 to 1. And of course, when we are using rebar, you need to give a stress strain relation for rebar as well. So here for rebar, I have used an elastic and a perfectly plastic model. There are many other models used by many other authors, like bilinear stress strain relation is used. But this is ideal. And the elastic properties are modulus of elasticity 2 into 10 raised to 5 Newton per mm square and Poisson ratio of 0.3. So with this input parameters, let us model the beam. Okay. With this, I come to the end of the presentation. Now, let's move on to the software and model the beam. Actually, I have already modeled this, and I have also already run the program, because modeling usually takes more time, and of course running a nonlinear analysis is very time consuming. It takes more than maybe 6 or 7, 8 hours for running the program. It depends on the size of your model. And of course, to get a proper crack propagation and proper stress results, you need to have a coarse and fine mesh. And of course, making your mesh finer will increase the computational cost. So I'll take the software. Is it visible?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay, I don't think much explanation is not is required to introduce the software. Is it required, or shall I move faster? You need to explain this in detail. Of course, this is an advanced course, so I think more explanation is not required on modeling and all. Anyway, I'll briefly explain each.
Sir, just explain the screen. That is,
Yeah.
students are there.
Okay. 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 ABAQUS. This is the user interface of the ABAQUS software. So you have different modules. This is the model tree. So you can access each of the module from the model tree as well as from the module itself. So you have different part, property, assembly, step, interaction, load, mesh, optimization, job, visualization, and sketch. So the initial step is to create your geometry. So creating your geometry is done in the part. So when you change the module, automatically the parameters for defining the icons automatically changes. So since we are dealing with reinforced concrete, you need to model the concrete as well as the reinforcement. So for that you need to create part. So this is where you create part. So I have already created different parts. Bottom rebar, since you are having a different area of cross section for uh, the bottom bar, top bar, and the stirrup, you need to create each part separately. If all are having same, you can just create one. Now to save the computational time, I have only modeled the quarter of the beam. So you can actually create part by clicking this create part. Then you have to give some name for the part. You need to choose the modeling space, whether you are doing a 3-dimensional model, 2D model, or axisymmetric. And type, you are having a deformable, you can model a rigid body, and the shape solid shell wire. So for a concrete, you need 3D, deformable, and a solid. So when you click that, this model will directly go to the modeling space. There you will create the dimension in XY plane. Once you create that, they will ask to extrude the other dimension in Z. And once you input all those dimensions, you will get the concrete model. Once you create this concrete, the other part is the rebar. So for rebar, the rebar is actually 3D deformable. It's not a solid element. it is a wire element. So there you can create the wire by specifying the length of this reinforcing bar. Similarly, you can create the top bar as well, and stirrup. Here I have, since I have used only the quarter of the model, I have used only the half the stirrup. Now once you have created all the models, all the parts required for the concrete beam, that is the concrete, the bottom bar, the top bar, and the stirrup, the next step is to assign material property for the created parts. So this is where we input the nonlinear properties for concrete. So you have to input the material properties for steel as well as concrete. So material 1 is actually the input parameters which is given for concrete. You need to input elastic properties, which is the modulus of elasticity and Poisson's ratio. So as I mentioned, I have given 22 gigapascal and 0.2. Now one thing you should note in ABAQUS is that you don't have any units. The units is based on the user. So if you use one unit, that unit should be consistent everywhere. So it is better to use Newton meter. So here everywhere I have used Newton meter. So this is 2.29 into 10 raised to 10 Newton per meter square, and 0.2 Poisson's ratio. Now if sometimes you require to input density if you are using implicit or explicit analysis, whereas for static nonlinear static analysis you just require elastic properties and the non-linear properties. You don't require to input density, but if you are using an implicit or explicit schemes, you require to input density. So you need to input density for concrete. Now since this model is based on concrete damage plasticity, you need to input the parameters related to plasticity. As I have mentioned, the dilatation angle, the eccentricity, the ratio of biaxial to uniaxial compressive stress, the parameter K, which defines the failure surface, and the viscosity parameter. So once you input all this, you need, these are concepts on plasticity. Next, you have to input the compressive and tensile behavior. So compressive response is yield stress versus the inelastic strain. So you need not input the initial the elastic response. You have to input the yield stress corresponding to inelastic strain 0, because up to the elastic yield stress you have already given this value. So you have to input only the inelastic strain. Elastic strain is not required. Then the tensile behavior. Tensile behavior, yield stress versus cracking strain. Now apart from this, you also have damage parameter. Damage parameter DC for compressive and DT for tensile behavior. The damage parameter, as I said, it is a function of plastic strain, and this damage parameter varies from 0 to 1. That you will get from the sub option, compression damage. So in compression damage, a damage parameter with this inelastic strain is equivalent to this. So this value varies from 0 to 1. It is better to avoid the value 1 because you will face some numerical errors. So it is better to give up to 0.9. or 0.99. Similarly, you have damage parameter dt for tension damage also. Here also this is a function of cracking strain. Now once you input all these values, you click OK, then it will be created. However, this material is not assigned yet. This we have just created the material. Now the material 2 is for the steel. So for steel, the Young's modulus, Poisson's ratio, and also the plastic. So here I have assumed a perfectly plastic and a yield stress of 450 Newton per mm square. So this plastic, you take it from this mechanical plasticity plastic. Similarly, the concrete damage plasticity and cement. These all are available in mechanical plasticity option. So once you define all this, I have also created one more material for steel plate, because you need to support this. It's not good to provide boundary conditions on nodes, because you may face with you may have stress concentrations. So to avoid stress concentration, I have modeled a steel plate at the support as well as loading plate, loading point. So you also have to create a steel plate, and for that I have given this need not be modeled. You just need to you just have to model it as a linear. You don't have to give nonlinear properties for this. So just a linear properties for steel. Then once you create these three materials, next is to assign these materials to the created parts. So for that, all the parts you have created will be seen here. So first you have created the concrete. So it will be, the part appears like this. And after you create the material, you need to create section. So section for each. Section 1 is actually concrete. So there you create section. You can give a name for the section like concrete. You choose the type solid and type homogeneous. So here all the material we are considering it as homogeneous. If you are using plane strain elements and all, you need to use plane strain. There are other types like Eulerian and composite and all. Whereas for steel, bottom steel, the steel plate and top bar and stirrup, you need to take the beam element. The beam, the type is beam, and you need to take the truss, because you are modeling the reinforcement as a one-dimensional element. So you need to take truss, which is a one-dimensional element for the rebar. So for rebars, bottom bars, top bars, and stirrup, you need to choose category beam and type truss. Beam is required for a beam element. Rebars is not having any bending stiffness. It is only having axial tension. So you just have to, you need to model it as a truss. So once you create the sections, you need to assign the sections to each of the part. So here I have created a concrete section. So for that, I'll click this, select the model, and choose the section. For concrete, I have chosen solid homogeneous material 1. So once you click that, the color of this part changes. This shows that this part is assigned with the defined material properties. In such a way, you can assign all the sections for bottom bar, the plate, that is the loading plate, and of course the stirrup and the top bar. So once you assign all the material properties to this parts, the next is to assemble all the created parts. So assemble is by creating instance. So each of the parts will have instance. So all the created parts will be available here. And again, when you create parts, you can create instance type as dependent or independent. Dependent means you need to move to the part to mesh. Whereas independent, you can mesh on the instance. So if you choose dependent, and if you create mesh on part, all the instance under the part will be, you just have to assign one mesh on the part. So all the instance under that part will get meshed automatically. But if you choose independent mesh on instance, you have to mesh each instance separately. So I have already created the part. Once you, when you add each of this part, this won't be located at the required positions. So you have to, you need to use the translation options, rotating options, etc. to. So I'll just show you how this each of the bar and the stirrup will appear when I add this. Now if I add concrete, this concrete is at the position itself. You need not change. But when you add bottom rebar, you can see it is observed at this origin. So this bottom rebar, you need to shift from this to the bottom, actually bottom of the concrete beam. So once you know the coordinate of this, coordinate of the bottom rebar, you just have to translate from this, from the origin to the required position. Similarly, the plate is also, when you create part, you define the coordinates for creating this part, right? So this will be at that location. So you need to translate this from the origin to the required point. So I have created two instances for this plate, one for loading and one for the support. So by knowing the distance, you can translate from this origin to the required position. Similarly, the stirrup. So here stirrup, it is not oriented also. So you can, once you apply this, you can use rotating instance option. So once you click this, you can rotate this, can click, select axis or start position. So you need to rotate this about this axis. So we'll choose this axis to rotate the start point and the end point. Then you need to specify the angle of rotation. So if you specify 90°, you get this instance get rotate. So once you create each of the part, the instance, and move each of the instance to the required position, your model is ready. Once your model is assembled, the next module is to create the step. Step defines what type of analysis you are going to perform, whether a static analysis, whether a dynamic implicit or dynamic explicit. So in the present, I have used a nonlinear static analysis. So when you create step, here is the option for creating step. You can define a step name for the step, and here you can find different. steps available. So here I have chosen static. You need not have to provide any time period. Time period 1 is enough. Whereas in incrementation depends on your type of loading. See, if you are giving especially for nonlinear static analysis, the time increment to reach an uh, solution equilibrium, this may take more number of increments. The time increment will be very low, maybe of the order of 0.1 into 10 raised to minus 3, etc., to have a converged solution, to reach the converged solution. So sometimes you require more number of increments. So you can specify 1000 or 2000 increments with an initial of 0.01, minimum 1 into 10 raised to minus 7, and maximum 0.05. So abacus will automatically choose the time increment based on the convergence required. It's not better to use fixed, because fixed, if you are using fixed, you have to use a very small time increment for convergence solution, and it is time consuming. Whereas if choosing automatic is will run the software very fast. So once you define the step, uh, you can also create a history and field output. That is what all results are required. Field output includes like the stress distributions, the stress components, stress in each of the direction, sigma 11, 22, 33, stress invariance, and you also have other stress parameters like meso stresses, etc. So you can get each of the stress distribution for, if you want stress distribution for each increment, you can give n equal to 1. If you want the stress distribution for every 20 increments, so if you are giving n equal to 1 for each increment, the abacus have to develop results, so it will be time consuming. So based on your requirement, you can give uh, the increments. So here I have chosen stresses, strains, the total strain, the plastic strain, the displacement, U translation, and also the failure, the compression damage, the tension damage, the shear damage. So once you define this, this is actually field history output. Similarly, you are having, this is field output. Similarly, you are having history output. Now, history output is normally used uh, to create uh, the output for a single. You can create output for the whole model, or you can create input for a set. You can create a nodal output. For example, if you are interested in displacement at the center, you need to create a set and choose a node which is at the center. And you can so when you create set, all the sets created will be available here. So once you choose that set and choose the displacement, so for each increment you will get the displacement value. So directly you can plot the load versus the time. Directly you will get from the output. So here I have used two history outputs. The one is the deflection. So I have asked for an output for every 5 increments. The displacement U1, U2, only displacement U2 is called, because we are interested in the displacement in the y direction. So I have only used U2. See, even this inputting this parameters will also affect your computational time. So only the parameters which you require need to be given. and the other one is the forces, the reaction forces. So you need to plot load versus, if you want to plot load versus displacement, you need the reaction forces. So I have also chosen that for every 5 increment. So once you input these two, the next module is interaction. Now this is an advanced topic, interaction. Since here you are modeling steel and concrete, the reinforcement steel is actually bonded to concrete. Now you have just created a concrete model and a steel model, but this is not bonded. So you can use constraints option for bonding this steel reinforcement, the stirrup, all together with the concrete beam. So here you can see in constraints you are having different options like tie constraints, rigid body, coupling. For modeling reinforcement to concrete, you have an embedded region constraints option. So when you choose that, the software will ask to select the embedded region. So you need to select the embedded region. So here you cannot select. So what you need to do is you need to hide this concrete. So you can access this model from the modeling tree. So this is the model. Here you can see assembly. In assembly, you can see all the instance you have created. So in instance, you can hide the concrete too. So first I'll remove this so you can see the. So this is the created the reinforcement cage. I'll hide the plate also. So is the reinforcement cage created. So you create constraints, embedded region, select the embedded region. So you need to select the embedded region. Select the embedded region. Once you select the embedded region, they will ask to select the method for host region. So host region is not the whole model. You need to select only the concrete. So you click select region, and here you need to hide this. Again, you need to select the concrete. You have to unhide the concrete. Show. You select the concrete region. So once you select that, you need not change the default values for weight factor, tolerance, etc. So once you create that, you can, this constraints is created. So once you create this embedded region constraint, this reinforcement will be bonded to the concrete. Now, as I said, to avoid stress concentrations, I have created top and bottom plates. Now again, you need to provide contact boundary conditions for these two plates. So for that, first you need to create interaction property. So in interaction property, you have different interaction like contact, cavity, foot cavity, fluid exchange, acoustic impedance, etc. So in that you will choose contact, and you can define a mechanical normal behavior. Tangential is not required because you are actually giving a vertical load. So normal behavior, and you can use pressure overclosure as hard contact, and you need not allow separation after contact. Once you create this interaction property, this will be available here. The next step is to create interaction between this plate and the concrete. Now to create that, you need to create interaction, surface to surface contact. So for that, you need to create surface. Which surface are going to contact? So before that, I have already created surface. Tools, surface. To create surface, go to tool, surface, surface manager. I have already created surface. Again, surface, you can create surface based on geometry and mesh. So here I have created based on mesh. So if you want to create surface based on mesh, you need to first mesh the model and then go to the interaction. So I'll explain how the meshing after this. So here you can see I have selected this area for surface 1 and surface 2. I have taken the surface for the plate. So if I hide the concrete, you can see surface 1 is for plate. You have to select individually each of this, and surface 2 is for the concrete. If you hide the plate, you can see the area which it is selected. So once you create the surface 1, surface 2, surface 3 and 4, you need to assign the surface to surface contact for this area. So that is done by creating interaction, surface to surface contact. So they will ask to select the master surface and the slave surface. So here master surface I have taken as surface 1, that is for plate, and surface. Once you create the master surface, they will ask to choose the slave surface. So slave surface is the concrete surface, which I have defined earlier, surface 2. So you have to create two interactions, one for the support and one for the load point. So once you create this surface interactions, I think the interaction modules is with that would be enough. The surface interaction and the embedded region constraints. The next is meshing. So this is very important. So the mesh, before assigning mesh, you need to choose what type of element you are going to use for this. For rebar, as I have mentioned, we are going to use truss elements. So you need to choose the element, assign element type, select the regions you want to assign, and choose the element here. So here you will have different types of element, acoustic, beam. So when you click each of this element, the description will be given here. B31, a two-noded linear beam in space. So we will be choosing truss. Truss is a two-noded linear 3D truss element. So T is 2 is actually the degrees of freedom. 3D is the three-dimensional space. T is the truss. So once you choose that, you assign this to the rebar. Next is the concrete. Now for concrete, the element type used is 3D stress, continuum, three-dimensional, 8-noded with reduced integration. So it is an 8-noded linear brick reduced integration with hourglass control. So once you choose the type of element for each of the part, the next step is to assign seed. Assign seed is the option how you need to discretize the element. So you can either create the model Or you can create seed. Seed means you can select each of the edges of the model, and you can specify based on the you can give a factor on based on the total model, or you can even give number of elements required for each of the edges. So here I have chosen 0.01 as the global uh, 0.01 times factor of the global size for meshing. So once you create the mesh seeds, the next step is to mesh the part. So you have to mesh each of the part separately, the concrete, the reinforcement. So once you mesh, the next is to create load and boundary conditions. Now this is very important. You may have convergence problems when you don't specify correct boundary conditions. Now here I have specified a pressure loading for the plate around 1 into 10 raised to 7 Newton per meter square. And this is the amplitude is ramp from 0 to this value. So based on the increment you have given, the ABAQUS will automatically solve for each load increment up to 1 into 10 raised to 7 Newton per meter square. So when you choose this pressure, ABAQUS will ask to select the surface. So you can directly select the surface. Done. Then you need to input the magnitude, then click OK. Then you will assign the loads here. Next is the boundary condition. So here I have created 1, 2, 5, 4 boundary conditions. The first boundary condition is the pint support for the plate at the bottom. So here this edge I have applied a pint support so that this beam can rotate about this edge. You have other boundary conditions as well. And the second boundary condition is, since I said I have used the quarter of the model to save the computational time, this face is not allowed to move in the x direction. So I have given a boundary condition u1 to be 0 for this face, whereas this beam is allowed to move in y and z direction. The third boundary condition is for this loading plate. Since this is a 3-dimensional model, you need to provide boundary condition for the plate as well. You just assigned surface to surface contact for the plate, but not boundary conditions. So I have given u1 and u3. u1 means direction along x, 2 means direction along y, 3 means direction along z. So the displacement along 1 and 3 direction I have assigned 0. So this plate is not allowed to move in 1 and 3 direction, but it is free to move along y direction. The last boundary condition is for this face. Since this is the quarter model, I have given u3 as 0. You need not look into ur because this is a 3D element. You are not having any rotational degrees of freedom. So displacement along the third direction is 0. So once you assign all these boundary conditions, your modeling step is over. You have assigned part, created property, assigned property, you have assembled each of the part, you have created step to define the analysis type, you have created interaction for reinforcement bonding and for contact of the plate, loading plate and support. You have created load, created mesh. So with this, your model is done. The next step is to create the job for running the analysis. So to create job, you can give a name for the job, and here you need not specify anything. You can directly click OK. Now, if you are using a supercomputers, you can increase the speed of the analysis by using multi-processors. And if you have a GPU acceleration, you can click this to speed up your computation. Normally, a PC will have 4 processors, so you can use 4 processors. But the problem is that if you use 4 processors, you cannot run any other program in the background. But the analysis will be more fast if you use the 4 processors. For supercompute, for workstations, you may have 8 cores, so you can use up to 8 cores and all. So once you create the job, you can submit. So I have already ran this program. It took around 6 to 7 hours to reach the load up to the failure. So I'll show the results. I have run 2 models, one for flexure and one for shear. So first I'll show the results for flexure. So this is when you go to the results, this will directly go to the visualization module. So here also you are having the model tree. So this is the option for plotting the contour. And each of the results will be shown here. The output variables which I have given was the stress, the plastic strain, the displacement. So first let us see the displacement. So this has been loaded up to a displacement of 0.02 0.2 meter. Similarly, you can you can visualize for each time step as well. For each time increment, you can see how this displacement varies and how the beam gets deformed under each increment. So increment, now the increment is 800. So you can see how the beam gets deformed under each increment. Similarly, you can take the stress distribution. Here you cannot see the stress distribution because the stresses in the reinforcement is higher. So you can hide that reinforcement to see the stress distribution. Again, you can remove this grid to properly visualize the stress. So you can see how the stress varies. So here up to this, up to step increment 40, it is somewhat linear, beyond which the beam behaves non-linear. So this is actually the meso stresses. Now let's see the damage. I have also opted for damage parameters. So this damage parameter will give you how each of the element gets damaged. So this is one way representation of the cracks. So you can see how this beam fails. Finally, this fails by tension. So you can see all of the element has reached the damage parameter. So this is flexure failure. And the another way of interpreting the crack is by plastic strain. So you can take maximum principal plastic strain. Again, you can run this, you can animate this if you want. So you can see how this the strain is initially starting from the center of the beam, and how, since this computer is very slow, you cannot see the other. For supercomputers, you can see how each of this, how cracks is propagated, flexure cracks are initiated, and how this is moving towards the shear cracks. So finally, this is failing by tension. Similarly, you can look into the stresses of the steel, whether steel has yielded or not. So for that, you need to remove this concrete and go to stresses, add this. So you can see, finally, you can see we have given a yield stress of 450 Newton per. So steel has yielded uh, at an increment of around, from, I think it is, yeah, at an increment of 720. At 740 the steel started yielding. That means when you are having a displacement value of around 0.03, 3 centimeter, 3 centimeter, the steel started to yield. As I said before, I have created an history output for the center node, so that you can plot that using the XY data. Create ODB history output. There we have already created the node for the deflection and the reaction force. So you can get, so this is the point, it will go up to linear. Then when it reaches the ultimate load, you can see the curve gets flattened. Now this graph is actually load versus displacement versus time. Now if you need load versus displacement, you need to take these values. This is time versus displacement. So you can take this displacement values, you can copy to your Excel or any graph plotting software, and you can also plot the force. So force you can get it from here. So this is the time versus force. So force versus displacement you will directly you can plot. Now I'll show you the other beam. Now this was for flexure. I've already run the problem for the shear as well. So for shear beam, I have shown that the support was near to the span with a shear span of 1.25 meter. So in here, we'll observe how this fails. So we'll first check the damage parameter. So you can see how the cracks or each of the elements get failed. So here you can see material fails by a shear crack. And as I said, the another way of seeing the crack pattern is by using the plastic strain. So with this, I think we come to the end. Is this okay? If you have any doubt in the presentation or modeling related to this, you can ask.
Hello.
Yes, ma'am.
I have a doubt. The
Okay.
stirrups, spacing, cover, etc. are default values, or we have to give it
No, that we have to create.
at
That I
the
have.
after bar, creating the top bar, bottom bar. After that, we have to specify. I think you didn't explain that. That is why I'm asking.
This we have already created, right? Part we by
Okay.
knowing the cover itself, we have created this geometry.
Okay.
Once you create this geometry in the assembly module, you are directly going to place from this origin to this.
Okay. There
This
you
this
are.
stirrup is already created in the part.
Okay. Okay. Then
We are
what?
only assembling here.
Okay. Spacing also. Okay.
Yeah, spacing also uh, we have actually created one part, right?
Okay.
So you can repeat this by using this linear pattern. When you click this linear pattern, you can select this and you can
Okay.
create the pattern along the XY direction.
And the support conditions are also given by boundary conditions, whether it's
Yeah, yeah. In the
indoor like that, only by giving the boundary conditions.
yes, yes.
Oh,
Yes, sir. Hello,
Yes.
sir. How will you specify the details of bars and then stirrups and all those things?
Yeah, in the part you have created the geometry for this, right? For bottom bar, uh, top bar and all. In property, you are creating sections. So in sections, when you create this, you can specify cross-sectional area here. You choose the material and you can define cross-sectional area for each created part here.
Like for stirrups,
Yeah, stirrups. This is for bottom, the stirrup. So for each of the part, you need to create section and then assign this section and material to the created parts.
okay, okay. Sir. Thank you.
So this is very important when you use units. So here you can see the area is in meter square. That is why it is in point, not. So unit should be consistent everywhere. Else you will face with error during the analysis.
Hello, sir.
Yes.
Sir, the values of damage T and damage C, is there any scientific way to get to those values? Because different papers are saying different readings.
There is no specific way. That depends on how you get the result. You can use different models and see which is matching with your experiment.
Okay, okay. And second thing, sir, if you want moment of inertia, bending moment at one particular section, does it calculate with respect to steel also, or only when it is an elastic?
Bending moment.
So suppose I want bending moment about half the length of this particular span.
Huh.
Can I get that value? Because we need moment to get steel design. So in SAP and ETABS, we will get moment at every point.
Yeah.
Similarly, can we get in ABAQUS?
In moment, no, because this is a 3-dimensional stress analysis, right? You won't get moment directly.
Oh, okay, sir. Thank you, sir.
Okay.
So what will be the difference in smeared modeling? Like, is it only in the input parameters?
Smeared modeling, as I said, if you are using a monotonic, for monotonic loading, you can use smeared crack model. I think results, you won't have much difference, provided that the input parameters you use for both models are same. But the input parameters you give is defined in different. The other one is plasticity based, whereas this one is not the damage plasticity based, but this is not damage plasticity based. So that difference might be there, a slight difference. You won't have a major difference. This model smeared is you cannot use for reverse cyclic loading and all. For
Okay,
reinforced concrete, mostly damage plasticity model is used.
Okay, sir.
Good morning, sir.
Yes.
Sir, good morning, sir. This is Bala. Yeah.
Okay.
I have one
Okay.
doubt, sir.
Okay.
You are using the steel rod, is using a truss element. Why
Yeah.
you are not using the beam element, sir? In which situation we are using a beam or a truss elements which is suitable, sir? Is there
No,
any specification or any specific method? Yes, sir. Tell me.
because these rebars are actually they cannot take any bending.
Yeah, yes, sir. But they are giving
So
the yes. Tell me, sir. Sorry.
so no need to take beam element. If you are having some bending stiffness, you have to choose it as beam element. Here truss are, it can take only axial tension. So truss
Yes,
element
correct.
is the appropriate.
But some journals are shows some researchers shows the selectors best option to compare to truss element. Beam element is better. Just conclude beam element is better result, or it's that value is nearest to exponential result. Something it's closer to value. That's all is concluded. So that's my.
Maybe if sometimes if you are considering this cage as a whole,
Okay.
maybe if you're considering as an individual bar, it behaves like a truss. But when you behave it, when you consider as a whole reinforcement cage, maybe it behaves like a beam. That may be the reason.
Okay. So
But
another one is. Tell me. Sir,
yeah, but
sir?
truss is mostly
Sorry,
used.
sorry for my
FC.
voice.
Okay.
Okay. So another one is, sir, can you update this video? Can I get this video, sir?
Which?
That recorded video. Your seminar video. This seminar video. In my mode of any form.
What video? I didn't get.
Maybe you are uploaded or some link or something. Anyway, because it's very useful for most of research scholars and some research students, sir, I think, and maybe MS students or MTech as well as PhD scholars.
Okay,
So
this modeling.
Yeah, modeling and this seminar, whole seminar, this recorded 1 hour session. This session.
I think this session will be recorded. I think this session is recorded.
Just
yes,
recorded,
sir.
but
yeah, you can.
Yeah,
how can we get, sir? That's
yeah, we will be sharing this video.
Sure. Thank you, sir.
Yeah.
Thank you very much, sir.
Yeah. Okay.
Sir,
Yes.
so I have a question about the ABAQUS software.
Okay.
So I have read that there are ABAQUS CAE, ABAQUS explicit and all. So are they linked or do they have their own functions?
No, ABAQUS CA is general, which include all analysis procedures.
Okay,
General,
can we do test simulations in ABAQUS CAE?
Test simulations means?
Means for we are doing some test in the laboratory. So can we simulate the same thing in ABAQUS and get the results?
Yes.
Okay, I have another question. We can do geotechnical analysis in this also, right?
Yeah.
So do you know what all parameters can we get from this?
Geotechnical, the problem is, see, if you are considering the soil as a whole, as a elastic, with one elastic material, see, soil you are having different, in different layers, it is different, right?
Yes.
So that I think it would be difficult, but still I think you can do it, but people go for software like Plaxis for doing geotechnical.
Okay. Okay, thank you, sir.
It depends on your problem. If you are for like a soil structure interaction, if you are more interested on response of the structure, then you go for ABAQUS. But if you are more interested in getting soil related effects, then you need to go for Plaxis, because in Plaxis you are having more options for soil modeling.
Okay, sir. Thank you.
So anyone else is having any doubts? No.
Okay, if no more questions, I think we'll wind up the session. So I take this opportunity to extend a special thanks to Mr. Muhammed Aslam for handling the session. And this was very informative, and this will certainly help participants in their research or projects works or whatever. So thank you so much, sir, from the part of our department, and
Thank
all
you.
the best for your research work, ongoing research works. Thank you,
Thank
sir.
you. Thank you.